All right, so what we're going to do is look at some basic functions, some, the functions we're used to, like we're going to look at a constant function, t to a power, sine and cosine and exponentials to see what the Laplace transforms are. And these are not only functions whose transforms are kind of easy to get to, it's also the functions that we're going to be seeing from time to time. So the first one we're going to do is look at f of t equals k, where k is a constant. And I just have these all written out because I know we've been through this before. It's just evaluating a bunch of improper integrals. So we know that the Laplace transform of k is the integral of k e to the negative st from 0 to infinity. And notice I wrote the limit notation here. So we take the antiderivative k e to the negative st, evaluate, and that is k over s. And I just want to make sure you know that I myself am not going to make you memorize the Laplace transforms. I will warn you, it will happen. You'll remember these, I'm sure, but you'll be provided with a table for any kind of graded assignment or graded test. So that's basically the Laplace transform of a constant. So moving ahead here to e to the at. So a is any number, and the Laplace transform is going to be handled slightly differently. So notice here, we can combine. And that means we have this integral right here. And again, if my goal was to make sure that the integral converges, I need to make sure that this is negative. So I need a minus s to be less than 0, which means s is greater than a. So that's going to be the domain restriction on the transform. Not that the domain really means a lot to us, but that's where the transform is going to be valid. So we go through the integral just like we have before. We substitute, we go to infinity for b, and that's going to make the first term wash away. That's going to be something that we notice from time to time. And we end up with 1 over s minus a. So this is the transform of e to the at. So just to kind of solidify this result, Laplace transform of e to the at is 1 over s minus a, where s is greater than a. Okay? So that is the constant function and the exponential function. So there we have that. So looking at transforms of sine and cosine. And again, these are just integrals again. You might remember from calculus that the integration for e to the negative st sine and e to the negative st cosine basically require 2 steps of integration by parts. You end up having to solve for the integral. I just went ahead and got the formula for them because I just thought that was easier. And you go through, and the Laplace transform of sine of at is a over s squared plus a squared. This again assumes that s is greater than 0. Oh, I do have it written at the top. Okay, and the Laplace transform of cosine is s over s squared plus a squared. So notice, they're very similar to each other, which, based on our experiences with sine and cosine in this course so far, that shouldn't be a surprise. So, kind of interesting. Now for the one that takes the most time is the Laplace transform of t to the n. Now, just realize that we've already done the Laplace transform of t to the 0. And that Laplace transform is 1 over s. The Laplace transform of k was k over s, let k be 1, and that's the Laplace transform of 1. Now, why am I making a big deal out of that? Let's go to Laplace transform of t, and now notice we have to do an integration by parts to find that integral, so I'm actually going to go through with it because there's something important that happens here. So here's your u and your dv, okay? And then we rewrite our integral, so this is the uv minus the integral of v du, okay? And notice that the first part we're just evaluating at infinity and 0 because that's what we're going to end up doing after we find the complete antiderivative. And then we know that the remaining integral is really going from 0 to infinity. That's not going to change. Now, the thing to look at, though, is, first of all, notice I skipped a step here. It's minus integral v du. So it's minus these two multiplied together, but minus a negative is positive. If I remove the 1 over s, this is the step to really pay attention to right here. We know that that integral is the Laplace transform of 1. So I don't need to reinvent the wheel. I already know that that's 1 over s. So we end up with 1 over s times 1 over s, which is 1 over s squared, which is telling me that the Laplace transform of t is 1 over s squared. Now, why is that important? Let's move ahead to n equals 2. Okay, with n equals 2, we go through one swing of integration by parts. Normally, we'd have to do 2 in order to get to the final answer, but notice something. You go through your u and your dv, and you make your substitution and blah, 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 and we end up here. Wait a minute, that integral is the Laplace transform of t, because if you're integrating from 0 to infinity, whatever you're multiplying by e to the negative st, that's the function you're transforming. So we can go right to this step right here, and we end up with 2 over s to the third. And at this point, you're probably noticing, hey, there's a pattern going on here. A power pattern, I guess I wanted to say there. So think about how t to the third would play out. You'd end up going through your thing, you'd end up with a 3 in front instead of a 2, but then you're going to get a 3 times the 2. So Laplace transform of t to the n, let's see where we've been. So when we transformed t to the 0, we got an s in the denominator. When we transformed t to the first, we got an s squared in the denominator. When we transformed t to the second, we got a third power in the denominator. So whatever power you are transforming, you add 1 and put it in the denominator. Okay? Now what's going to become of the numerator? Well, you're going to end up with, let's imagine Laplace transform of t to the fifth. You're going to end up with 5 times the transform of t to the fourth, which is 4 times the transform of t to the third. You're going to end up multiplying all the integers together. And what are you going to get? You're going to get a factorial. So the Laplace transform of t to the n is n factorial over s to the n plus 1. And just a little summary. So if k and a are constants, n is a positive integer, this is the table of transforms we have done so far. So we can just use these. Now, how are we going to use these? In the next video, which will be the third of 3, we're going to talk about how to find Laplace transforms of sums, differences, and constant multiples of functions. And if you go back to when we learned derivatives, you're going to notice we're kind of taking the same tactic here. The Laplace transform is an integral, so that means if I have a sum of two functions, we should just be able to add the transforms. And that's exactly what's going to happen. So come back for the details. Thanks for taking the time to watch.